Continuing our study of integration by partial fractions, let's take a closer look at the case of non-repeated linear factors and see more examples. Let's say we want to integrate the function x cubed minus 4x minus 10 divided by x squared minus x minus 6 between 0 and 1. As we know, for a quotient of two polynomials, the first thing we have to check is whether the degree of the top is less than the degree of the bottom. In this case it is not, and that means that the first thing we have to do is long division. So since we've already discussed how to do long division, I'm not going to do that in detail this time, and simply give the result. We divide x cubed minus 4x minus 10 by x squared minus x minus 6, and we find x plus 1 as a quotient and 3x minus 4 as a remainder. You can check the work in here, and this is probably a good exercise for you. So that means that we can rewrite our function as x plus 1 plus 3x minus 4 divided by x squared minus x minus 6, and in this latter fraction the degree of the top is less than the degree of the bottom. The second step is, of course, to factor the bottom. So in this case you see that, for instance, negative 2 is a root. That means that we can factor x plus 2, and the second factor is x minus 3. Because we have only linear non-repeated factors, the decomposition into partial fractions has the form a over x plus 2 plus b over x minus 3. In this case we can use the n-cover method to find a and b. Namely, to find a, we're going to multiply by x plus 2 and set x equal negative 2 to make this x plus 2 0. And when we do that, x plus 2 cancels out on both sides, and the factor with b, we have b times x plus 2, which is 0 when x is negative 2. Therefore these terms cancels out. On the left and on the right hand side we only have a, and on the left hand side we have the value of what remains when x is negative 2, and that gives us negative 10 at the top and negative 5 at the bottom, in other words 2. Therefore a is 2. To find b, we're going to proceed similarly, multiply everything by x minus 3 and set that equal to 0, in other words plug x equals 3. When we do that, x minus 3 cancels out at the bottom on the left hand side, cancels out when we have bx minus 3 over x minus 3, and in the terms containing a, when we set x equals 3 it gives us 0, so that we have only b on the right hand side, and on the left hand side the value of what remains when x is 3, which is 9 minus 4, 5 at the top and 5 at the bottom, in other words 1. Therefore b is 1, and that means that our fraction can be rewritten as 2 over x plus 2 plus 1 over x minus 3, and therefore our integral is the integral from 0 to 1 of x plus 1 plus 2 over x plus 2 plus 1 over x minus 3. At this point we have to be a little bit careful, because now we are about to use the fundamental theorem of calculus to say that this definite integral is simply the difference of the values at 1 and at 0 of an antiderivative of this function. And in doing so we are making the assumption that the function is continuous on the interval 0, 1. Since we're dividing here by x plus 2 and by x minus 3, we have to make sure that we don't have any discontinuity of the function in the interval 0, 1. Here we have no problem, because the discontinuities are x equal negative 2 and x equals 3, which are not inside the interval 0, 1. Therefore the fundamental theorem of calculus applies, and this integral is the difference of the value at 1 and at 0 of an antiderivative, which we can pick to be x squared over 2 plus x for the antiderivative of x plus 1, plus 2 natural log of absolute value of x plus 2, plus natural log of absolute value of x minus 3. When we plug 1 in this function, we get 3/2 plus 2 ln of 3 plus ln of 2. When we plug 0, we get 2 ln of 2 plus ln of 3. Simplifying, we obtain 3/2 plus ln of 3 minus ln of 2, which simplifies further as 3/2 plus ln of 3/2. Let's look at another example. We want to integrate 2x plus 3 over x squared plus 3x minus 4. Degree of the top is already less than the degree of the bottom, so no need for long division. And then the natural next step would be to factor the bottom. In this case, it factors nicely as x minus 1, x plus 4, and that means partial fractions decomposition for that is of the form a over x minus 1 plus b over x plus 4. Remains to find the two coefficients a and b, and then integrate both partial fractions separately. Certainly we can do that, but partial fractions is a little bit more time-consuming than substitution. And usually before you embark on using partial fractions, you should check whether you can obtain your integral more quickly using substitution. And in this case, you see that what we have is really integral of du over u, where u is x squared plus 3x minus 4, because of course in that case du is 2x plus 3 dx, which is exactly what we have at the top. So we obtain directly natural log of absolute value of u, which in this case is just natural log of absolute value of x squared plus 3x minus 4 up to a constant. And there is no need to look for coefficients. Now one more example. Let's say we want to find an antiderivative of 4x plus 3 divided by 2x squared minus 5x minus 3. We can start by checking for substitution. You see that the derivative of the bottom is 4x minus 5, so we cannot get 4x plus 3 as a constant multiple of 4x minus 5, so substitution wouldn't work. The degree of the top is already less than that of the bottom, so there's no need for long division. So the next step is to factor out the bottom. And in this case, you see that, for instance, x equals 3 is a zero of that quadratic function, because if we plug x equals 3, we get 9 times 2, 18, minus 15 minus 3, so we get 0. Means x minus 3 is a factor. And to get this 2x squared, we need 2x in the other factor. To get negative 3 for the constant, we get plus 1 for the constant term in the other factor. So we have 4x plus 3 divided by 2x plus 1 times x minus 3. We have only non-repeated linear factors, so the decomposition into partial fractions has the form a over 2x plus 1 plus b over x minus 3, where a and b are constants to be determined. Here we can use the end-cover method. So to find a, we multiply everything by 2x plus 1 and set that equal to 0. In other words, set x equal to negative 1/2. And when we do that, 2x plus 1 cancels out on the left-hand side and at the bottom of a. And the other term would be b times 2x plus 1 over x minus 3 when x is negative 1/2, so that gives us 0. So on the right hand side we have only a, on the left hand side we plug x equal negative 1, equal negative 1/2. So we get 4 times negative 1/2 is negative 2, plus 3 gives me 1 at the top, and at the bottom we have negative 1/2 minus 3, which is negative 7/2. So we have 1 over negative 7/2, that's negative 2/7 for a. Similarly, to find b, we multiply by x minus 3 and set that equal to 0, in other words, set x equals 3. And in doing so, x minus 3 cancels out on the left-hand side and below b, and the term containing a becomes 0 because we set x minus 3 equal to 0. So we have only b on the right-hand side, and on the left-hand side the value of what remains at x equals 3, which is 12 plus 3, 15, divided by 2 times 3 plus 1, 7. So b is 15/7, and that means that our integral is really negative 2/7 of the integral of dx over 2x plus 1 plus 15/7 of the integral of dx over x minus 3. I'm going to pull the 2 at the top of negative 2/7 inside the integral, just so that I have at the top the derivative of what's at the bottom. So you have to be a little bit careful when the coefficient of x is not 1 in your linear factor, because then you have a small substitution to do. Namely, here u is 2x plus 1, so we have an integral of the form du over u, where we have adjusted the coefficient at the top to get du. So we obtain negative 1/7 of the integral of du over u, where u is 2x plus 1, plus 15/7 of natural log of absolute value of x minus 3, all this up to a constant. And of course, integral of du over u is simply natural log of absolute value of u, and u is 2x plus 1. So this is the antiderivative we obtain. Now turn to the next video to look at the case where we have repetition in these linear factors. In other words, when a linear factor appears several times in the factorization of q, something like x minus 1 cubed, for instance.